Bivariate data relates two quantities x and y that may be changing together. In this section, we'll create graphs called scatterplots of bivariate data. Below is a scatterplot of calories versus fat grams for some common fast food items. A scatterplot simply takes an x and a y together as a coordinate pair and plots them. So one of these dots represents the highest amount of calories here, the Burger King Whopper. The x is the horizontal and the y is the vertical. So if we go over 33, okay, and then up 584, we should find the highest number of calories of all. This dot right here represents the Whopper. Let's look on the list for the fast food item that has the lowest number of calories. That would be the chicken tenders. Only 223 calories and 12 grams of fat. So go over 12 and then up to 223. This dot represents the chicken tenders. Now what we're looking for in these types of graphs are trends. So when the fat grams of an item increases, what tends to happen to the calories of the item? Well, we see that as we go to the right, we're going to larger and larger values of fat. Then as we go up, we're going to larger and larger amounts of calories. So as the fat grams increase, we see that the calories tend to increase too. This is called a positive correlation. There are other terms we can use to describe correlation. Positive correlation is used when we see an upward trend. Negative correlation would be a downward trend. Linear correlation means that a line is the best mathematical model for the data. High correlation means the data fits a mathematical model almost perfectly, whereas low correlation means it doesn't fit the model very well at all. What type of correlation is shown in each of these diagrams? Well, this first one shows what we call no correlation. That is where the x's and the y's seem somewhat random and we don't really see a clear trend at all. Dots are kind of all over the place. This next one, the data looks like it could fit a line somewhat. If we were to draw a trend of the data, it appears to be sloped downward. For that reason, we'll call it negative and also linear. Even though it's not a perfect line, a line could be a good mathematical fit for that data. And we might say low or moderate. It's kind of a judgment call. Why do I say moderate? Because it doesn't fit a perfect line. And the data's not all over the place though either. Something in the middle. This data doesn't look very linear. It looks like some kind of parabola or other curve could fit the data better. So I'm going to say nonlinear. When it comes to the correlation, you might say moderate to even perhaps high. When it comes to this data set here, we're going to call this perfect. positive correlation. Why is it perfect? Because it fits a line perfectly. Why is it perfect? Because it fits a line perfectly. Why is it perfect? It fits a line perfectly. Why is it perfect? It fits a line perfectly. Why is it perfect? It fits a line perfectly. It's positive because we could imagine ourselves walking on this as if it were the terrain of a cross-section of Earth. And we always think about ourselves walking in the positive X direction, but as we walk, we would be going uphill. And for that reason, that's why we call it positive. And it is certainly linear. The next one's similar, but it's not perfect correlation. I'm going to call it high correlation. It is linear and positive. The next data set is fairly spread out. However, it is conceivable that a line could be used as the best mathematical fit for this data. So I'm going to call it low correlation. And we would call this negative. The reason for that is as we walk across this cross section as if it were a cross section of Earth, we would be walking downhill. That's why it's negative. And we could argue that it's linear as well.